Yep, that's my fault. Thank you. All right, you should be able to hear me now. I just have to turn on my mic. So thank you, and I appreciate the tag team effort to make sure this live stream thing and in person is working, so appreciate it. All right, so today what we're going to talk about is we're going to be talking about design criteria for programming languages and abstractions in programming languages. So two pretty distinct concepts. Is there a way I can make this bigger? Yeah, sure. Okay. So we're going to start with the language design criteria. Okay. So our questions here are kind of relative to designing a programming language. So what would we consider good programming language design? What criteria should be used to judge a language? And how should we judge success or failure? Right? So basically, if you ever want to build your own programming language, the first thing you need to do is know how to evaluate. Evaluate what criteria you will measure success against. And so even if we're not building our own programming languages, we can still use these techniques to evaluate other languages to kind of give us an idea of what languages are good, what languages are bad, and why. Or is it that absolute? So we're going to kind of set up a couple of criteria for what we would consider to be successful. And so it can be any of these categories. It doesn't have to hit all of them. It just has to hit at least one of them. So for a successful language, it will need to achieve the goals of its designers. It could attain a widespread use in an application area, or it could serve as a model for other successful programming languages. And not all of these are intertwined, right? Success can be quantified in different ways, okay? So for example, why are some languages popular while others are not, right? Because if one of the criteria for success is widespread use, then if a language is popular, it's successful. If it's not, it's not. A language like Java or a language like Python is widely successful just surely out of its own use, whereas a language like maybe Smalltalk is not a success because nobody used it. But a language like Smalltalk is hugely influential. It's one of the first object-oriented programming languages and had a deep and profound impact. It was a major influence on Java, and it was a major influence on the emergence of object-oriented programming. So is that a success? And so that's why I like having these criteria. If we're going to measure criteria by influence, then yeah, absolutely that's a success. If we're going to measure criteria based upon who uses this language, then it's an abysmal failure. And we can kind of pick and choose which one of these is applicable to our languages, right? If we want a language that's going to be widely used and we don't hit that goal, it's a failure. We have different categories of success. Is really the main point that I want to drive home. Traditionally, widespread use is considered to be a successful language, but you have other criteria that can apply as well. So when we're creating a new language, we really want to just decide on a goal and stick with it, right? Because we're going to have different design constraints and criteria depending on the goal. If we're trying to achieve widespread usage, well, we need to understand what the market is. What demands are there which could get our new programming language to be widespread? If we're trying to make something that does a specific thing very well, well, then maybe that will have a very big, popular kind of use base. Maybe it won't. Maybe it'll be a small little niche community of people who really love this for the thing it was designed to do, right? Is Scratch a successful programming language, right? I would say yes, because its goal is to be educational. It's very popular in that domain. We're not spinning up a new server with, Scratch, but that doesn't make it any less successful. So we got to make our mark and then aim for that. And that can be different depending on your language, okay? And as Scratch kind of goes with, it's especially important for special purpose languages. If your language has a specific kind of target audience or target application space in mind, you really kind of want to nail that. So basing off that kind of point, right, if we have different goals of success, we also want to be able to break down the focus areas of design in our language. We basically want to be able to not quantify, but qualitatively describe different aspects of the design of different programming languages. And we're going to use these focus areas to kind of give us a lens to analyzing individual languages. So our focus areas are going to be efficiency, regularity, security, and extensibility. Right? These are the 4 criteria we are going to focus on and utilize to analyze these individual languages. Jesus. So we're going to start with efficiency, okay? Now, typically, when we think of efficiency of a language, we are thinking computational efficiency. How fast can this language go, right? So there's a lot of factors that might go into this, right? There's a lot of different elements which make a language computationally efficient. And I will also note that we are going to treat languages as the general way that they are intended to be utilized. So for example, Java is a traditionally compiled language. So we'll take that into account when measuring efficiency. I talked about yesterday how, in theory, you could go write like an interpreter for Java and, translate the language that way. And that's still true. But we're going to ignore those kind of weird edge cases and possibilities when we're talking about these criteria. We're going to really just talk about the language as its designers provided. If it's provided as a compiled language, that's how we're going to speak about it. We'll take the compiler in as part of this analysis. So efficiency, right? Typically, it is thought of as just computational efficiency. And a lot of things you get in this realm are just how fast does the language go. So you have a lot of things typically seen in compiled languages which help with computational efficiency. Stuff like static data typing and force-stack compile time means that the runtime doesn't need to check data types before executing operations. Right? So if you have a compiled language and you make the compilation process do type checking, then you don't have to do it at runtime. If you don't have to do it at runtime, there's less to do at runtime. Runtime's going to go quicker. So you have a boost in computational efficiency, right? And there's plenty of examples of this, right? Where you have just different optimizations, right? Sometimes the compiler is able to optimize out your loops. C is notorious for this, right? The GCC compiler is incredibly optimized and will make your kind of code. It will simplify things, reduce things, understand the quickest way to get done what it is you are trying to do, right? So that's computational efficiency. How fast does it go? And that's not the only efficiency that we have. So there's computational, but there's also programmer efficiency, which we can define as how quickly and easily can a person read and write in the programming language. So I know people who are taking this class tend to have a pretty wide spectrum of what courses they have coming in. But for those of you who have taken, I don't know where it covered, but the SDLC, right, the software development lifecycle. The concept of the SDLC is just to kind of break down, the different portions of building a program. And, there's doing your research and then your actual development. But the biggest chunk is always going to be maintenance. In a real-world programming project, the biggest amount of time you're going to spend is maintaining an already existing application or program. As a result, the action of a programmer having to open up an already existing program, look through it, read and understand it, figure out what's going on so they can make a change and update it, is going to be the bulk of the work over the lifetime of this program, where the bulk of the work comes from. And so we have questions about writability and expressiveness and, well, I jumped the gun, so I'll just start here and then work backwards. Readability, right? So how easy is it to comprehend the computations in a program? So if you're spending most of the lifetime of a program trying to read through it, understand it, and maintain it, how easy that program is to read is a huge factor on how much time it's going to take to do any maintenance, right? So a language that is very programmer efficient might be incredibly easy to read, might be that you can just kind of look at this code that hasn't really been engaged with very much, understand very quickly what's going on, make your changes with ease, and then get out. And the less time you have to spend reverse engineering your code, the more time you have to work on other bugs. More programmer efficiency gets development done faster, right? So we also have writability and expressiveness, right? How easy is it to write things in your programming language? You know? So the quality of a language that enables a programmer to use it to express computation clearly, correctly, concisely, and quickly, right? And expressiveness, how easy is it to express these complex structures, right? So we have different languages throughout history that have different levels of, say, readability and writability. It is really great if your program is very easily readable, but if it's also incredibly verbose and very difficult to write, then you kind of have this trade-off, okay? And it really opens up, one of the things about these programming criteria is they are in competition with each other often enough, right? The difference of these different angles of programmer efficiency don't always play nice, right? Sometimes writability sacrifices readability and vice versa. One of the classic examples of this is Perl, a language I have not really worked in because I just haven't had the need. But the old kind of joke lying around the internet has always been whether or not you can read a Perl script is highly dependent on if you wrote it. Because Perl is just so easy to just write a one-liner of nonsense that is super powerful, does an incredible amount in a very small amount of code, but God help you if you didn't write that because you'll never know what's going on. PHP is similar from my experience. I remember reading, oh, PHP is a nightmare. Oh, it's not bad. I was deving my little web dev box. Totally super easy. And then I had to go back 3 weeks later and fix it again. Impossible to read. I had no idea what anything meant. So sometimes readability and writability are in competition with each other. And you kind of have to balance them or take your pick. So some examples, right? So the conciseness of the syntax also contributes to efficiency. So for example, older programming languages like Pascal had literal begin and end keywords to signify the beginning and end of block structures. We decided that was bad, and now we just have symbols for it, which is a much more synthesized and reasonable way to go about it. Okay. Readability, right? How easy it is to comprehend the computations in the program. Now, I do need to keep myself on pace and on time, but there is a small story about this, and that's COBOL. Because every couple of years, there is somebody else who has the bright idea, you know what? You know how we make programming more accessible? We make it more like natural English. We make it more like English, so that way people don't have to know how to code. They can just type in expressive sentences. COBOL in the 1950s had this idea. AppleScript in the early 2000s had this idea. It continues to just kind of crop up. And you know what? It's a terrible idea, and it's a miserable experience every single time you do it. Because computers and compilers are not witty enough to translate natural language, this thing that is so overwhelmingly filled with ambiguity. Humans have a hard time understanding each other. The whole point about diplomacy is saying just enough vagueness that you can defend your position later when you change your mind. Like, that's an art of human speech, is to be ambiguous. Shockingly, computers don't love that. So when we try this, we end up getting into a situation where we try and make them, so they get super wordy, and there's a lot of human words, so the programmers hate them, right? Because there's no normal syntax and everything's super verbose. But non-programmers still don't understand what the hell is going on, so they abandon ship too. And you just get these kind of Frankenstein-y language that no one wants to work in, like this. I hate this, right? Now, granted, about half the country's unemployment systems are written in this. So if you're willing to kind of work with this, they've been pulling people out of retirement and giving some pretty hefty salaries to any young person brave enough to be like, yeah, sure, I'll sign up for a 70-year-old garbage language. Let's do it. So like, this is an example of what not to do. But yeah, efficiency. So programmer efficiency has a really important role to play Even though the traditional way of thinking of efficiency is computational, programmer efficiency is a very serious consideration to have. Also, we can consider reliability, right? You can consider reliability of a program to be an efficiency issue. So basically, if it's easier for you to make mistakes in a language, it could be seen as less efficient, right? C is a lot more computationally efficient when it works. And that's a big if, right? And there's a big reason why we've moved away from just doing everything in straight C, okay? Now, yeah, kind of as I mentioned, right? Reliability can be affected if restrictions are not imposed. One of the classical examples of why C is such a nightmare is the complete abundance of pointers. C is the language, like the quintessential way to describe it is C is a language that will give you as much rope as you want to hang yourself with. It'll trust you right up until then. Like, it's just like, oh, but you asked to do this ridiculous thing. I wasn't going to tell you no. Of course you know what you're doing. That is the C programming language in a nutshell, which if you do know what you're doing, that can be very empowering, really great. But as much as we all like to think, and we do know what we are doing, you know, mistakes get by. And we really would like the compiler to be like, yo, heads up here. You may have done this wrong. C compiler's not interested in that. It's all or nothing. And that isn't great for reliability, right? Other languages, more modern ones like, say, Java, just were like, you know how it'll make it more maintainable? Don't do that. Don't touch pointers. Not good. So kind of speaking on this point, right? Because again, these criteria do overlap, kind of, you know, tease at each other. The other one I want to talk about, another one I want to talk about is security, which is closely related to reliability. So a language designed with security in mind discourages programming errors and allows errors to be discovered and to be reported. So in this context, security doesn't mean like cybersecurity or anything like that. It means the language's ability to detect invalid things at compile time and tell you about it, right? Or at the very least, for interpreted language, not execute the code, as opposed to a language like C, which will do the ridiculous thing, and if it corrupts memory, it'll just use corrupted memory. You know what I mean? If you try and write the wrong type of data into a byte in C, it'll just write that data there and then reinterpret the data the other way later and just cause nightmare on nightmare. Python, although it is interpreted and can't give you a compile time error, when you try and do that type of data X into data Y, it'll crash. Not as nice as a compile time error, but certainly a lot better than just getting output that doesn't make sense and having no idea where or why something went wrong. So that's the kind of notion of security, whether a language can prevent the programmer from doing something that is not allowed. Okay? So types, type checking, variable declarations all result from a concern for security. On the other side of the coin, an exclusive focus on security can compromise the expressiveness and the conciseness of a language. Yes? So Python's typing thing, and we'll get to this in a couple of weeks, but it kind of depends on what angle you're coming at it from. So relative to like a language like Java that does a lot of compile time checking, it's not enforced at all. It'll just run the code. But compared to a language like C, it will get unhappy if you try and move the wrong type of data into a different type of data's location. If it's expecting one thing. Now, it's a weakly it is a dynamically typed language, so variables don't have data types, so you can just move data in there. But if Python's ever expecting a number for something, and then you give it something that isn't a number, it will crash, as opposed to C, which will just reinterpret the bits and just wing it. So it's like a sliding scale. So like relative to like Java, it's not really checking data types. It's letting you put whatever you want in a variable. But if you try and like pass a function, a int, when it's expecting not an int, it'll get upset. Yeah. Yeah, that's what it is. Yeah, no, it's because it's dynamically typed. But we do have a couple of weeks of Python, but that's in a little while. But that's the idea. Sorry. No, you're all good. It's a good question. So yeah, right. so this type of security, right, going to that full step kind of starts to hit a wall here, right? Because if you start sacrificing the expressiveness or the readability of your program to make sure everything is just tip-top perfect, it's kind of rough, right? So it's a spectrum, right? Trying to add as much security as we can without losing the readability, writability, and expressiveness of the underlying language. So we could call a language that is secure semantically safe, right? And it's semantically safe means that a language that prevents the programmer from compiling or executing any statements or expressions that violate the language definition. So for example, an array out of bounds exception, right? And so we have semantically safe languages, okay? So the nice thing about semantically safe is it prevents a programmer from compiling or executing statements or expression that violate the language definition. So ideally, compiling, right? The more things we can kick to compile time, tell you this line at this space, not going to work, fix it now. That's way better. Executing kind of worse. You have to execute the code. But at least when you execute it, you get a crash, not a C or C++ of I'll just do it and see what happens, right? Array out of bounds is a prime exception. Go out of bounds on a Java array, crash the program, get told why, get told what line of code it happens in, get told what the invalid index was. Do it in C, and you just modify that memory, and if anything does go wrong, you just seg fault. That's way worse. I hate that. Thank you. So like having semantically safe languages, or at least relatively semantically safe languages, right? Because you can have languages that catch most things, but maybe there's a couple really weird odds and ends or edge cases that slip by. Not ideal, but as long as you're mostly semantically safe, anywhere from mostly to fully, completely semantically safe, you're in good company. You're in a good spot. So security is really important, right? So that gives us efficiency, both programmer and computational, as well as security, how a language prevents the programmer from doing things they're not allowed to do. The third topic, the third criteria that we're going to discuss here is regularity, right? So regularity refers to how well the features of a language are integrated with each other, okay? Greater regularity implies that we have fewer restrictions on the use of particular constructs, fewer strange interactions between constructs, and fewer surprises in the way languages behave. Okay? Languages that satisfy the criteria of regularity are said to adhere to the principle of least astonishment, right? So regularity is the most hard to pin down. I'll just kind of put that out there. It's the one that's, I think, the most kind of in space, so to say. I really like this grounding, right? The principle of least astonishment, right? You can, just by looking at the language, kind of intuit what goes where and what comes next because you understand the rules of the language, and those rules are consistent, okay? That's what we're trying to adhere to. Yes?
Another issue with PHP that it's inconsistent.
Yes. Wildly, yes, and that's exactly right. It's incredibly irregular language. I don't actually have any PHP examples of here, but PHP is a prime example of that. Different elements of PHP look, act, and behave in wildly different ways to the extent that it almost feels like different languages all kind of glued together, which is also one of the reasons why it's such a nightmare to go back and read PHP. So I like the least astonishment principle because I think it's the one that's just a very natural way to kind of conceptualize what we're talking about here. And as kind of your counterweight, human languages are the literal opposite of this, right? The fact that we are like I before E except after C, or except the 80% of the time that rule isn't real. Wait, sorry, right? That type of nonsense is what English is built on. And that, again, nightmare for computers. So pretty much we're trying to go in the complete opposite way of natural human speech, right? And the goal of having this least astonishment language is that language constructs should be simple to understand with few ambiguities, right? Now, it turns out we can actually break regularity down into 3 subsections, okay? So we can have generality, we can have orthogonal design, and we can have uniformity. So generality is achieved by avoiding special cases in the availability or use of constructs by combining closely related constructs into a single, more general one. Okay? Orthogonal design is that constructs can be combined in any meaningful way with no unexpected restrictions in behavior. Basically, constructs should be the same when they're used in different contexts. And uniformity is a design in which similar things look similar and have similar meanings while different things look different. All that just kind of sounds like a lot of vague, abstract stuff. So we're going to tie all of this to actual physical examples. Okay? So first, let's start with generality. A language with generality avoids special cases wherever it can. So for example, operators. Should operators be applied consistently and to new data types? Right? So that's kind of our question. So in a language like C, right, C cannot directly compare 2 structures with equals equals, so the operator lacks generality, right? It's not really general, okay, because it has special cases. Sometimes behaves and can behave. Other times it's just not going to work. What about Java? Do I have that as a note? Okay, yes, I do have that as a note. So what about Java, right? Let's just use the equals equals sign. Would that be general or would it not be? Now, I would argue it would be because it behaves the exact same way for custom-defined data types as built-in data types. Now, granted, we say it's the equals equals operator, and that's a terrible name. But if we just called this an identity operator in Java, right, then it would be general, right? Because it just checks the identity of 2 reference types or the identity of 2 primitive types. And if the identity is the same, you get back true. And if the identity is different, you get back false. It has the exact same behavior, whether it's a built-in reference type like a string or it's a custom-made data type. And so we could say that this equals equals in the Java language has generality because there aren't any special cases. You could push back and say that because it's called the equals operator and it behaves a little differently for reference types and primitive types, that's a non-generality. And now you see the kind of nightmare about this, right? Because this is qualitative, not quantitative. You can have debates and you can have argumentation, and it's not necessarily a line in the sand of this is correct and this isn't, right? This is a little bit more mushy. And that really does come from the fact that pretty much universally we're trying to apply these post the language's creation. Maybe they were used as like a guiding factor in some way or another, but these are not the basic building blocks of the universe that all the languages were built upon. This is just a useful way to analyze languages, which in a lot of cases have already been made. So sometimes the lines where things start and end are blurry and not particularly definitive, and you kind of have to make arguments for them, which is not something particularly common in computer science. It's not a way that computer scientists really like to engage with stuff, so I find it interesting to do it in here. So that's generality, and so now orthogonality, right? So orthogonal design allows language constructs to be combined in any meaningful way with no unexpected restrictions or behaviors arising as a result of the construct's interactivity with each other, okay? So in a language that is truly orthogonal, constructs do not behave differently in different contexts. Right? Restrictions that are context-dependent are non-orthogonal, and restrictions that apply regardless of context exhibit a lack of being general, right? Because it's just either you have a restriction based on context and it's non-orthogonal, or you have a restriction that is always there and it's not general. Again, these things sometimes are in competition with each other. So an example of orthogonality is function return types. So in Pascal, only scalar or pointer types can be used as a return value. Now, we don't really need to know what the heck those are, right? We don't care what a scalar is at the moment. The point being is that it's a subset. Only some things can be returned. So if we imagine we had the return keyword, right? That return keyword is non-orthogonal because the context, what we're trying to return, changes the behavior of the return statement. It only works if the data type is a subset of all valid types, right? So depending on the context, the type of the return value, it either works or it doesn't. Thusly, it's non-orthogonal. Same thing with C++ and C. It's a lot more convenient than Pascal in that it allows a lot more data types to return, but there is still a restriction that array types cannot be returned. Thusly, there is a context where the return keyword behaves differently. Thus, the return keyword in C is still non-orthogonal. Now, it's a lot less of a pain because it is so general overall, but it is still non-orthogonal because there is a context where it behaves differently. Whereas Ada, Python, and Java, anything can be returned. And so the return keyword is orthogonal. It acts the same regardless of the context. Another is placement of variable declarations, right? C actually requires local variables be defined at the beginning of a block, right? And that placement restriction is contextual, right? So another is primitive in reference types, okay? And Java is notorious for this, right? In Java, your primitive types use value semantics, while objects/reference types use reference semantics. And so there is a contextual difference on how variables and data structures and everything works depending on whether you have a primitive or a reference type. There is a major violation of orthogonality in Java, severe. It is inundating at the core of the language. The way Java gets around this being super inconvenient is it adds some hackery. It adds boilerplate garbage on top. So for example, array lists. Because generic types in Java can only work for objects, they can't work with primitives. Array lists and other object-based data structures, which is most of them, can only store reference types. Now, they get around this huge non-orthogonal restriction by doing boxing and unboxing. They say the language will automatically convert your primitive types into reference types and vice versa, so you don't have to worry. There's a massive lack of orthogonality, but we'll just deal with it behind the curtain. I mean, I guess it works. Yes?
It kind of seems like you have to choose orthogonal or security. Is there one that's like more important than the other?
I would say it's less that one's more important and more that it's important to strike a balance, right? If you have a language that is hideously non-orthogonal and doesn't have Java-esque, patchwork to do it, it's going to be incredibly frustrating because you're not really going to understand what's going on, or you're going to need to know a lot of contextual information for it to make sense. That being said, same with like security. If it's a language like C where it just kind of throws you to the wolves, you're going to be in a bad time. So it's about trying to find as much of a compromise between the two, and depending on the type of language. If you want your language to be a little bit more, less safe and just kind of qualify that, be like, hey, it's very orthogonal, it's very easy to work with, but there are a lot of pitfalls, be wary. Then that works too. It's just a matter, one, I wouldn't say is better than the other. You want to have a little bit of both, but as long as you strike a balance that you understand you're striking, you should be good. Does that make sense? Okay.
That's an interesting subsector.
Yeah.
I know developers who work extensively in Java.
Oh, yeah.
And it's interesting because some of them decide to use basically eschew primitives altogether because they complicate things.
Right, absolutely.
And so they basically, for practice, enforce slightly more orthogonality.
Which is really interesting. Yeah, sometimes languages get so big that they become language subsets where people kind of tweak the rules a little bit. Because yeah, exactly. I mean, it's one of the big kind of takeaways is that Python, which is really the OO that came a decade after, did away with primitive types. really, in my opinion, the Java's inclusion of primitive types is a concession to the early 90s, where people were still very worried about efficiency, to a kind of, maybe not ridiculous then, but at this point, 2021, with all the processing power we have just lying around, a ridiculous notion. And it is kind of an antiquated side to Java. So I think that's very interesting that there are dev environments where they're just foregoing it and kind of changing how they work with the language. Because, yeah, this stuff can have a pretty serious impact. Oh, and lastly, parameter passing, right? In C, the default is to pass parameters by value, but when an array is passed, it's passed by reference. Having a language that, depending on the context of the data type, passes differently, whether it's a value or reference pass, not fun, because you just have to know that, right? There's no way to understand that by reading the code if you don't just know that's what happens. That's going to be hella confusing the first time you have to encounter that. Now, lastly, we have uniformity, which is just the consistency of appearance and behavior of constructs. So basically, we want similar things to look similar and different things to look different. And if you have a lack of uniformity, then similar things look different and different things look similar. So for example, same things looking different. Right? C++ requires a semicolon after a class definition, but forbids its use after a function definition. Holdover from C, I'm pretty sure. So like, just, you don't want that type of differentiation, okay? So different things look the same. And I had to dig for this because like, different things looking the same is something we try and avoid and has generally been kind of phased out from most programming languages, but there are some old examples here. So Pascal uses the name of the function to return the function's value, which is a little insane to me, but that's what they do. So this is different things look the same. You have a return statement here, and yet you would have to make a call to GCD to do a recursive call. Right? So what's the difference between a return statement and a recursive call? Different things look the same. Yikes. There's a reason this isn't a common thing anymore. This is bad. I don't know why Pascal did that. Another different things look the same is C's use of the asterisk operator. Are we multiplying or are we dereferencing pointers? Now, this one's so fundamental that you kind of get a knack for it pretty immediately when you engage with C, but that is a huge difference, right? If you really don't know what you're doing in C and you're just trying to jump in and you start seeing this same operator getting used in wildly different contexts, meaning wildly different things, it's not great. So, yeah, and that's it for the uniformity. So just overarching regularity or irregularity. Many irregularities are case studies in the difficulties of language design. So for example, that extra semicolon problem I mentioned earlier, it's a byproduct of the need to be compatible with C, right? Which is the kind of the whole bit of C++, right? It's going to be C, but with object-oriented support and some more modern features, right? And yet, to sell the language, they still wanted to include that C support. So instead of just cutting whole cloth and starting anew, they built on top of something else, and that came with some baggage. Hence, your irregularity, right? And I already talked about that, right? I think on the other side of the coin, you have the example of a language like Swift from Apple, where Apple, being the corporate monolith that they are, don't really care what people think, and had the ability to say, like, we had a language, and we're completely throwing that into the waste bin, and we're going to start a new language, and y'all are going to learn the new language. And I don't care if you don't like it, because what are you going to do? Not many companies or people or language designers have that type of strong arm, just ability. Because if you just tell them, oh, we're changing the language completely, deal, they'll just go to a different language. They'll go to a different platform. They'll leave you in the dust. Apple's one of the few entities that's like, you're not leaving. So, yeah. So our last one here is extensibility, right? So we have an extensible language as being a language that allows the user to add features on top of it. So for example, the ability to define new data types and new operations. This, at this point, is pretty fundamental to all programming languages, they all need to be extensible because that type of extensibility is the underpinning of modern software development. Don't reinvent the wheel. Yeah. You know, you can extend built-in features with new releases. You can allow user-defined types. Now, very few languages allow additions to the underlying syntax and semantics. So you can use the existing language as it is to add new functionality, but you can't actually add anything that grows or modifies the underlying language itself. An exception to this is Lisp. Lisp languages typically allow new syntax and semantics via a macro. This is really fascinating, as it's one of the only languages that really, it's where the idea comes from, and the idea of defining new syntax on the fly is pretty radical, which is why we'll talk about it in a lot more detail in a couple of weeks. Yes? I'm going to go with no. It kind of, I'd have to look a little bit more into it, but I'm going to go with no on that context just because it is built into the language. It's just kind of giving you a little bit more flexibility. When we see macros, we'll kind of see how we're literally adding new semantics. But I want to look at duck typing a little closer before I was 100% on that. Python's such a weird language because it's such a smorgasbord of everything. It's like usually the answer is no, but sometimes it just has this wild feature that allows you to do some specifically weird thing. So Python's hard to kind of know off the cuff. I don't think so, but I'd have to double check. So in our last 8 minutes, we're going to go over quickly some abstractions in programming languages, the language design criteria covered, and so now we just want to quickly talk about some abstractions. So we have 2 types of abstractions here, data abstractions and control abstractions. And these are really the core of why we have high-level languages. It is to abstract away stuff from the programmer so they don't have to deal with it, or at least not deal with it to the same degree as they would have to pre-abstraction. And we can also attempt to categorize abstractions by levels, okay? So we have basic, structured, and unit abstractions. Basic being the smallest, structured being like a middle tier, and unit abstractions being the largest. Okay? So we're going to just kind of talk. We're going to have 6 categories, right? Mix and match the 3 and the 2. So we're going to start with basic abstractions, right? So basic data abstractions are things such as hiding the internal representation of common data values. The actual hardware is storing ones and zeros. Right, when I store an integer value, I'm technically storing a series of ones and zeros into computer memory. And you can't engage with that underlying data representation. Maybe you can do some bit operations in C, but like short of that, most modern languages, you don't get to touch that internal representation of your data value. It's abstracted away. Less for you to work with, less for you to have to understand, more energy to focus on other things. Variables. No more loading and no more storing to individual memory locations. Just store it in a variable using a symbolic name. Data types and the process of declaring a variable, same principle. Standard mathematical operations, same principle. Instead of having to implement the mathematics through machine language, we can just use algebraic syntax. This, in fact, was the key feature of Fortran, which was the first compiled language to ever really exist. One of the big reasons it came into existence was, I want to do algebra. I'm tired of having to load, store, add, right? I do occasional work in my own assembler project, so I have things to say about assembly language sometimes. We also have data structures, right, where we're collecting related data values into a single unit, and we can hide the component parts, right? But the parts can all be accessed and modified from the structure. So for example, right, we have like a structure and a record or an array or a text file, right? Like in the array, a sequence of individually indexed items with the same data type. So our abstraction here is that instead of having to actually just remember all either the variable names or worse, the memory addresses of a collection of memory, we can simply remember a single memory address which is abstracted away in the form of a variable just to a name. And then we can allow the language to calculate the offset from that location to the specific element in our array or other collection, right? We abstract away remembering where the collection is located and where things in the collection are located in terms of computer memory, and simply just remember the name of the structure and maybe the index of a value, right? Abstracting away all that hardware and just having to remember the high-level logic. Now, unit abstractions are things like information hiding, right, where we define a new data type, right? In Java, that's kind of one of the cruxes of object-oriented, right? It is a private data with a public interface. That combination of private data is abstracting away, you know, kind of having to remember all this loose data and just collecting it into a single entity, which can then be stored, okay? So unit abstraction itself is often associated with the concept of an abstract data type, okay, where we have a set of values and the operations on those values, and we can separate the implementation from the interface. So for, say, like ArrayList in Java is an abstract class. You can make an ArrayList of type X or of type Y or of type Z. The implementation does not care, right? But when we actually, so the implementation doesn't care, and then when we define a specific array list, we'll use the abstract data type to kind of substitute it all in, right? So again, it's kind of at a higher scale, but we're still just abstracting away work that we would otherwise need to do, okay? Abstraction also provides usability, reusability, because we can, you know, have an API, right? We can just kind of put everything into a package and then extend it in and use that. Okay. So let's talk about our control abstractions really quick. Okay. So we have some basic control abstractions. Again, use of algebraic notation, also syntactic sugar. Right? So it's not just that we have the most standard algebraic notation, it's also the fact that we have some clever algebraic notation, like plus equals, you know, to reassign a value. Right? Small little things that just kind of help us not just abstract away the machine language, but also help us abstract away some of the monotony of algebra itself. We also have structured control abstractions, right, which divide the programs into groups of instruction nested within tests that govern their execution, right? Control structures of sequencing, selection, iteration, branch instructions. So basically, we're abstracting away from the machine language need of just executing sequentially and having to manually implement your structures. In machine language, you want to build a loop, you got to set what the condition is, where you have to loop to. You have to kind of manually create the loop. You have to manually create your if statements. Structured abstractions abstract that away. These concepts of iteration and conditional branching, instead of being a manual thing you implement each time, you just use the pre-built structure and let the compiler do the work. Okay? Just your example, you go from this to this. I'd rather write this every day of the week. Okay? But that doesn't look like a joy to program. And then lastly, I'm going to just, I'm like out of time. That happens. I go rambling on. But basically just like we have procedures and we have functions, and really like instead of having to, again, direct the program counter to jump to another location, you can just have a function which does it all for you. The only difference between a procedure and a function is that canonically, procedures don't return values and functions do. A lot of times we use the terms interchangeably because pretty much everything in a modern programming language has the ability to return, and if it doesn't, it's like a void keyword. It's not like a different structure, but that's the technical difference. Functions return things, and procedures don't. And then lastly, unit abstractions, units, threads, processes, right? You want to do a unit abstraction, take your entire program, pop it on another thread, and run it simultaneously while you're running your other code. Look at that, it's 12:50, nailed it, right? Perfect. So that's it. Shit, knew that was going to happen. I was waiting for me to drop that. Have a good weekend, everybody. Again, no homework until next weekend. And if you have any questions about this or the other lecture, just let me know. Yes? Exam dates are posted on Canvas under the syllabus page. There's like the schedules. It's just some ugly ass text document, so I'm sorry about that. But it should have all the dates of when we're going to have exams. Absolutely. Also, thank you everyone watching the live stream.